So if you've been watching the videos on this playlist, we've talked a lot about the internal workings, what's simplest cases of what's going on inside of the machine. And in all those examples, we had an input. It was already there. And then we talked about what was going on inside the device and on the way to the output. So today, let's talk about inputs a little. So on the laptop where I'm making these, I have the keyboard there, the mouse touchpad. I can plug up another mouse to USB or something and move that around. And to us, it seems instinctual, right? We have buttons or something that moves. It seems fairly easy to use. Then we have things like the tablet here. I also have that on this laptop. It's a Flex, so one of those where it opens up to a laptop and then folds all the way, the screen folds all the way around to get a tablet. So touchscreen on there too, but this one's in front of the camera, so I can point at this one. But it seems like the more modern, fancier thing is going to be the touchscreen, right? We just touch the right spot on the screen to open a browser or close the browser, or touch the right, drag around the right spot on the screen to get the little messages that the tablet's sending me. And it's based off just where we touch on the screen. It seems newer and fancier. Actually, this is the easier one. So let's talk about this as far as inputs, because that's a very easy one. So today's video is about touch sensors. So let's go over that real quick. Okay, so to start with, we need to know about the pieces we're going to use. So we go way back here, back to before the days of digital things, just basic electronics. And there were only a handful of pieces that we had to work with. So the first one we're going to need here is a resistor. So our schematic symbol looks something like that, little jagged edges. And resistance is basically we're doing something with the electricity. So in the simplest circuit that's really easy to visualize, let's just say a light bulb. And some light bulb we're going to power, and you can put a switch in there. We plug it up to the battery and the light bulb comes on. Simple circuit. So the light bulb, we're doing something with the electricity. And that doing something with it creates a resistance to that flow. So resistance is when we do something with the electricity. And something we often have to do is simply adjust the levels to where we want them in a particular circuit. So for that, we have a little piece that we call a resistor, which just creates an arbitrary amount of resistance. It just does something, it just burns through some of the electricity arbitrarily to adjust our values. One of our most important pieces, so we'll need a resistor for this. Then the other one that's involved here will be a capacitor. The symbol looks something like that. So, like two T's butted up against each other, maybe. We're not describing the piece here in a minute, and it might make more sense where that picture comes from. And that's going to be a very critical one, because these two together did most of our analog circuit work before the days of digital stuff. It was RC circuits, resistors, and capacitors. Did most of it. We also have inductors and other pieces in there, but mostly RC circuits, resistors, and capacitors. And that's very important because I wrote touch sensor up on the label for today. But the technical term for this, I probably should have wrote capacitive touch sensor, because it works off of capacitance. So we need a capacitor and a resistor to create a touch sensor. So let's talk about a capacitor and what that does. So a capacitor is basically just two plates that are separate from each other. Two metal plates separated from each other. So we have some voltage running down a line. Then it's going to hit the first plate. We have a small gap to the other plate. And then there's another plate. So you might probably familiar with electricity going down that line. That one likely makes sense to you. Electricity just going through the line. Then it has to go across the gap here. And when it goes across the gap, it's going to create a field. It's going to switch from being a voltage in a line into an electromagnetic field, and then the other side's going to pick it up, and it's going to continue on down the line. But that field's not instantly there. Right? Electricity comes flowing down this line, which that one, I'm going to call that instant. It's still not instantaneous, but I think everybody's familiar enough with electricity that you'll be okay if I call that wire instantaneous, right? We turn it on, electricity's instantly on that wire. So wires, kind of like the difference between plugging your laptop up to the Ethernet versus Wi-Fi. Right? You're going to get a much better signal straight down a wire. It's a much better conductor than the air. So electricity is pretty much instantly across that wire, but then it hits the capacitor, and it takes time for that field to build up. All right? It's not that field, there's no electric field, and that field just has to kind of build up, right? And then on the other side, it's going to pick it up and continue on. But that time is the important part. And we can adjust that time. Because if we add some resistance in here, so after our capacitor, we add some sort of resistance in junction with the capacitor, then we can control that time, right? Because if something's happening on the other side, that resistor is going to drain some of the. I'm trying not to use too many technical terms on this because it's introduction stuff. But what's a good juice? That's commonly referred to for common term for electricity. So that resistor is going to drink up some of the juice and slow that down a little. And that's how our early ones worked. A resistor and capacitor, so we would put together RC filters. And to be technical, to be an RC filter, that happens on the way back to ground. So we have some stuff going on, and then on the way back to ground, just remember, current's always searching for a route to ground. On the way back to ground, we slow it down with an RC filter. And that's what we're going to use that concept to build a touch sensor. Okay, so with those analog circuits there in mind, we can build up a touch sensor. Back with analog circuits, before the days of digital, our main control, like I just said, was with an RC filter, with a capacitor trying to build up an electromagnetic field, and a resistor affecting the charge and discharge on that back to ground gave us a time value. And we can do stuff with that time value. Well, there's a couple things you may have heard before that we can use. The first off is humans are grounded. That's what makes electricity so dangerous, right? When we get into big currents, all the examples here, we're talking about small voltages, but when we get to big voltages, what makes them so dangerous, electricity so dangerous, is humans are grounded. Electric current is always trying to find the best path to ground, and through a human is a great path for current to get to ground. So that's why electricity can be so dangerous. You may have heard that before. You may have also heard that our bodies have resistance. So on my stick man here, I'm going to replace that with a resistor. Draw that a little bit better. The human body also has resistance. Not very much resistance, but some resistance. That's why a little bit of resistance. That's why it's a better route to ground than most of our circuits where we're doing stuff with high voltages. And a route to ground, so it makes electricity dangerous. But as you can see, we have this part of the circuit already. The human body is a resistor, and the human body is a route to ground. So that's half of our RC filter. Well, all we need to do is come out here with, say, the stick man's hand, 3, 4, 5. If the stick man's hand is one of the plates in the capacitor, we have an RC filter. And that's how a touch sensor works. That's the idea of a touch sensor works. So we set up half of the capacitor, and then we touch it. And optimally, like I said, we want a space there. So we can put something in between there. We'll grab a different color, maybe this will show up, maybe the red will show up. We put something in between there that is not a great insulator and not a great conductor. Something in between, so that we'll still get some effects to it, right? If it was a great insulator, it would block it. And if it was a great conductor, it would just make contact and we wouldn't have a capacitor anymore, we'd have a wire. So something that's not a great insulator or a great conductor going between there, excuse me, we call that a dielectric material. And for what this is leading up to, one good dielectric material would be a thin screen of LED, thin matrix of LEDs to produce a screen. Then it separates our hand from the other side of the capacitor, so we get the capacitance. And there's a gap there, so we get capacitance, and then the human body serves as resistance back to ground to finish out an RC filter. And that's all there is to these sensors. So let's go plug up a circuit and see how it works, and hopefully it'll make a little more sense. But it all depends on the time, because we're going to charge and then discharge this capacitor, and then that takes time, and we can control that time through resistors, through resistance. And then we can make use of that time because we can measure that time. We just set up 2 pins. So I'll describe the default one. We connect 2 pins. There's electricity flowing between them. It's almost instantaneous. Then we do this off to the side. So we connect 2 pins. That's not a very good picture. Let me redraw that. Maybe a resistor. So we connect 2 pins, and electricity flows between them. And it's like a wire, we might as well say instantaneous. Right? It's not exactly instantaneous, but very, very, very quickly. Happens very, very quickly. Well, when we create our RC filter, it takes time for that electromagnetic field to charge up and then discharge, and that time affects how long it takes electricity to flow from this pin to this pin, and we can measure that and tell if our human is touching the device or not, based off how long that takes. Because if they're not touching it, we don't have an RC filter, and the electricity is pretty much instantaneous between the 2 pins. And if they are touching it, well, then we do have an RC filter, and there's a time delay for the electricity to flow between those 2 pins. And that's all there is to a touch sensor. So let's go look at an example real quick, and a couple steps in the example to build up the code, and we'll look at that and then come back here and wrap everything up. So here's the circuit for today's example. I have a nano for microcontroller, and here I have pins 2 and 4 coming out. So 4 is sending a signal, which is coming over on this yellow wire, flows through this 1 mega ohm resistor, and hits this other yellow wire and back to pin 2 to register it. And connected to one side of that resistor, have a wire coming out down to what's going to serve as the touch sensor. So originally I only had just a little piece of wire coming out here, but it didn't, which is plenty enough, but it didn't show up very well in the picture. So I just extended that into a small coil, and then I wrapped that in Scotch tape. To express a couple points, well, what it's doing as far as capacitor
capacitance, like we talked about a moment ago, is now no matter how hard I press on that, there's a piece of scotch tape between my finger and the wires, so there's always going to be capacitance, right? There's always going to be some space between there because of, well, we call it dielectric material. It's not a conductor, and it separates the two sides of the capacitor. So no matter how solid the contact is, it's always separated by the tape. So I like to do that and kind of express the point that this simple setup would go right through plastic, paper, cardboard, stuff you can put nice little labels on. You don't have to touch the wire directly, which is probably a little closer to what you're familiar with the touch screens on phones and things like that. And like we discussed on the board, so when my finger comes in and touches the sensor, we get capacitance changing the value going through there, so the microcontroller will detect the difference of what it would be when touched and when not touched. And that's all there is to a touch sensor. And then over here is just an LED to indicate it's being touched or not being touched. So that's all there is to this circuit. Let's look at the code real quick, and then we'll come back over and see it operating.
Okay, so the code's going to come in 2 steps today. So I have this library. This is quite a popular one. It's just everything's set up to do what was just discussed on the board. We get that time delay, and then we can register the time delay. And this is just a library that's already set up for it, so we don't have to write all that in the code ourselves. So it's already written. We just go ahead and use what's already written. So just bring it in the library, creating an instance of it. And well, for this first part, this is something that's going to show up a lot, so I thought I'd go ahead and include it. The documentation on this is, like always with documentation, long and boring. So I got far enough to see how to initialize the object, and then get that time constant out of it. So for this first pass, all we're doing is just printing out the time constant to see what sort of numbers we have, and then figure out what to do with it. Instead of reading through tons of examples and seeing what they do, it's like, okay, I know it's returning a number representing the RC time constant, so I'm just going to see what that RC time constant is and then base my code off that. So I already uploaded this here, so I'm going to open the serial monitor. Well, the serial monitor would just print out the numbers. I'm going to go to the plotter and just look at the graph. So here, I'm not touching it. We can see it's kind of bouncing around from 0, hit 5, went a little past 6 a couple times. But now if I come over here and now I'm touching it, so while I'm touching it, it looks like we're way up here around 180. Let off of it, back down fairly small. Way down there when not touching it, way up there when touching it. So it's bouncing around, so obviously probably want to take a few measurements, enough to get a good idea. Looks like there's some high spikes and when it's not being touched, and some low drops when it is being touched. But there's a huge range that we can work with here. So after just a couple measurements, it looks like anything in this range right here would be good for a threshold. So it looks like 100's in that range. So I can just set up some code so that if it's that number, the time constant is greater than 100, it's being touched. And if the time constant is less than 100, it's not being touched. Seems like an easy way to set up the code and avoid reading through a bunch of examples and trying to figure out what they were doing. Just look at the numbers I need, or look at the numbers it gives me, and then I'll figure out what to do with them myself instead of copying examples. So that's the first part. So let me type up the code that's actually going to control the circuit, or modify this into the code that's going to control the circuit, and we'll look at that real quick. And now the modifications to the code. So these 2 lines are still the same. Just set up, ask for the library, and then set up an instance of the object. Then I added
a pin for that the LED is connected in and set that to an output. Then down here, instead of printing out the value that capacitive sensor object gives me, I'm just going to, already printed it out, saw what it was, so I'm just going to say if it's bigger than 100, turn the LED on. And if it's less than 100, turn the LED off. And then there was a delay here, which was just to make it easier to read the numbers when they print it out, so I took out the delay. And that's all the only modifications that go. So just getting the number, getting that RC time constant, checking to see if it's above or below a threshold, and then turning the LED on and off. So now let's go look at that circuit actually operating. Now that the code's finished and uploaded onto the microcontroller, just kind of the setup like we talked about earlier, these pins are connected across a resistor, which is, and they just detect the difference between them. The microcontroller is detecting the difference between those pins across a resistor, and when my finger comes in and gets really, really close to that wire, we get a capacitor, so then it becomes an RC filter instead of just across a resistor, so there's a lot more change. We detect that change and the light comes on, or let go of it, and yeah, that's all it takes to make a capacitive touch sensor. Just a simple RC filter. And then we register the difference in the time constant when not being touched versus when being touched. And we can do a lot from that. So that's all there is to that. I'll touch it a couple more times. And then could do direct contact on the wire. I like to just wrap it in plastic or put it on the other side of paper or something so that there's guaranteed to always be a little bit of space there to make sure it's a capacitor. But that's all there is to that. So here's that wire I had for the touch sensor and coiled up, and again the coiling up was just to show it better on the video. So if I uncoil it now, hopefully it'll make perfect sense how the straight one is going to behave exactly the same, and any spot I touch along the wire, we get that same effect, right? Hopefully that makes sense. Because the final part we need to expand that single touch sensor into a screen is to, instead of a coil, stretch it out into a wire, and then have a few of them. Make a grid of those touch sensors with it stretched out to a single wire rather than a coil. We can do the same thing. We can just check and see if one of those is triggered above or below a threshold. Maybe that wire went above the threshold, and that wire went above the threshold. Well, if that wire and that wire went above the threshold, then that means our touch happened right there. So we can quickly determine where on the screen that touch occurred. Or for another case, maybe we want to check a few touches, right? We get above our threshold on those two, that junction of wires, and then that junction in the array, and then that junction in the array a split second later. Well, that would mean we swiped right. Touched here, then split second later it triggers over here, split second later it triggers over here. That indicates we touched and swiped right. And that's how the touch screens work. So you can see it's a very simple piece, unlike the keyboard and mouse where there's a lot going on, right? For lack of a better term, we often think of a keyboard as primitive because, well, that's what we used in 1947 with the EDVAC machines, right? That's the original computers using those modified typewriters. But that's a mechanical piece. There's a lot going on just in the mechanical part, and then we have to process the output of that mechanical part. So the keyboard's actually more complicated than the touchscreens. Hopefully that cleared up any mystery around those pieces. The name of the playlist, Removing the Mystery, hopefully that cleared up how that works and what's going on with it. And that's actually the easiest way to get input into a